how many points of inflection does this function appear to have? In other words, how many places does it appear that the concavity changes? So think about that, take a look at it, see what you can do. One way we can think about this is we're trying to locate places where this graph is concave up versus concave down. And from negative infinity, for a while, this thing seems to be concave up because it's making, remember, concave up makes the U. So a lot of people say, oh, it stops being concave up here, or maybe it starts being concave up here. No. This part right here is all concave up. Everywhere on this U is concave up. So don't look for maxes and mins. That's not points of inflection. Instead, look for where that steering wheel stops turning one direction and starts turning another direction. If this is a map of a road, the steering wheel is turning to the left. Now it starts turning very sharply to the left. And then it starts straightening out, but it's still turning to the left, but then some point along the way, maybe, I don't know, maybe around there, that's when the steering wheel might stop turning to the left and start turning to the right. And so we've changed from concave up to concave down. This part right here is an upside down U. And then somewhere around here, maybe around about here, who knows, we stop turning to the right and start turning to the left again. So we don't see exactly where these points of concavity are, points of inflection are, these changes in concavity. We know that they happen somewhere there, and it appears that we might have two POIs. We don't know for sure, but it sure does appear that way. So the next question might be, what's going on with that second derivative at those points? So remember that the second derivative is positive, 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 all along here, right? That's what a concave up graph means, right? It's got a positive second derivative. Our slope is getting bigger, right? Our slope is very negative. Maybe our slope equals negative 10 or so up here, very steep and negative. And then maybe here, the slope equals 0. So our slope went from negative 10 up to 0. And then maybe our slope got all the way up to maybe, I don't know, maybe positive 5. I'm just guessing. But at this point, the slope stops getting bigger and it starts getting smaller again. So from a slope of maybe 5, it starts getting smaller. So let's go to orange, I don't know. So then our slope is getting smaller during this concave down period, right? It goes down to 0, and then maybe it goes down to something like maybe negative 1 right here, right? So our slope is decreasing from 5 down to 0, down to negative 1. And then our slope starts getting bigger again, right? And then, so during this concave up part, our slope gets bigger again. It gets back up from negative 1 maybe to 0 right here, and then gets very steep again. Maybe, who knows, maybe that's a slope of 8. I'm just guessing. It's just all approximations here. But, so the question is not what is the first derivative, that's what I'm looking at here, but what is the second derivative at those points of inflection? Well, remember that the second derivative is the rate at which the first derivative is changing, right? So we've got a positive second derivative, and then it changes to a negative. So assuming a continuous second derivative, which is safe to assume perhaps because this appears to be a polynomial function, so not only is the polynomial function continuous, but its derivative is another polynomial function, so it is also continuous. And then the second derivative is another polynomial function, so the second derivative is also continuous. That means that there are no jumps, no breaks, no points where the second derivative is not defined. We're going to go ahead and assume that if we're traveling from a positive second derivative to a negative second derivative, the intermediate value theorem would state that we would have to pass through 0. So it appears, we don't know this for certain, but it appears that f double prime of x equals 0 at these points of inflection. All right, good. So the next question might become this true or false question. If f prime of c is equal to 0, then c comma f of c is a point of inflection. And if it's true, I want you to explain why. If it's false, I want you to provide a counterexample. So after we've thought about this for a minute, hopefully we realize that this is a false statement, because same as the first derivative values, right? If we're checking a first derivative value, we set that equal to 0. That doesn't guarantee that that's a point where the first derivative changes signs. Same thing with the second derivative. Just because the second derivative equals 0 doesn't guarantee that it changes signs. Here's a nice example. F of x equals x to the fourth, right? F prime is clearly 4x cubed. So F double prime is clearly 12x squared. So there is a critical number at x equals 0 because the second derivative, it's a critical number of the derivative. So there is an x value where the second derivative equals 0, namely x equals 0. But the second derivative is positive to the left of 0. The second derivative is positive to the right of 0. It does not change signs. The second derivative stays positive on both sides. Therefore, if there's no change in concavity, there's no point of inflection. So again, same as with when we were checking for maxes and mins, we needed to see that change in the sign of the first derivative. Exact same process for second derivatives, finding the points of inflection. We have to find that change in sign. So we're going to look at the same examples we did on the last section. We found all the relative extrema. Now we're going to find all the points of inflection. So remembering that the first derivative is x minus 1 times 3x plus 5. Maybe since it's already in factored form, we'll do the product rule here. If you prefer to distribute and use the power rule instead, who am I to judge? You should get the same answer. So anyway, we've got 3x plus 3x is 6x. We've got 5 minus 3 is 2. And we're going to set that equal to 0. We're going to find that x equals negative 1/3 is the value where the second derivative change, or no, not necessarily, where the second derivative equals 0. So there's only one value on our f double prime line. X values that are smaller than negative 1/3 are going to give us a negative second derivative, and values bigger than negative 1/3 are going to give us a positive second derivative. So we can say that negative 1/3 comma f of negative 1/3 is a point of inflection because f double prime changes signs at x equals negative 1/3. We don't have to say changes from positive to negative or from negative to positive. We don't keep track of that as much for points of inflection because there's no distinction between them. There's still a point of inflection, whether it's concave up to concave down or concave down to concave up. We just don't generally concern ourselves with that. All right, keeping on, we're going to try this next one, the triggy one. We're getting triggy with it. And we take that derivative of the derivative, and we get our second derivative. The 1/2 is gone. The negative cosine goes to a positive sign, and we'll set that second derivative equal to 0. We're looking for x values for which sine of x equals 0. Between 0 and 2 pi, well, that's x equals 0, x equals pi, and x equals 2 pi. Right? Those are the values. And we don't really need to consider 0 and 2 pi because we can't consider approaching 0 from both sides, right? We have to see that change in concavity. And if we're not considering values to the left of 0, then we're not considering that second derivative to the left of 0. Likewise with 2 pi, again, that's on the end point, so we don't need to worry about that. But on the f double prime line, we can put pi. That's a value where the second derivative equals 0. The second derivative of the function over here to the left of pi, like maybe pi over 2, the sine of pi over 2 is 1, so that's going to give us a positive. We're concave up on that side. And maybe the sine of 3 pi over 2 over here is negative 1, so we have a negative here. So once again, f has a point of inflection at pi, comma f of pi. And for the same reason, because f double prime changes signs at x equals pi. Again, that key word there is changes. We have to see that change in sign. S-I-G-N, right? Once again, we have the first derivative already of this function. We did that last time. So we'll find the second derivative. We'll quotient rule this guy. And derivative of the top is negative 6x times 3 plus x squared minus 9 minus 3x squared times, let's see, 2 times 3 plus x squared times the chain rule is 2x, all over 3 plus x squared. Factor out, let's see, what can we factor out? We can factor out a 2x from the, maybe a negative 2x might be nice. We can also factor out a 3 plus x squared. Okay, so negative 6x turns into 3. We still have 3 plus x squared here. The negative is gone, the 2x is gone, but we still have a 2, so plus 2. The 3 plus x squared is gone, but the 9 minus 3x squared is still hanging out. And we've got that over, oh, this should be to the fourth, shouldn't it? Squared. So 3 plus x squared to the fourth. When we reduce, we get one of those goes away with one of these 4. And we can simplify in the square bracket there. So let's see, we've got 3x squared minus 6x squared is minus 3x squared. We've got, let's see, a plus 3 and a plus 9 and a plus 18 is a plus 27. And then that's still over 3 plus x squared, this time to the third power. Maybe I should factor out a negative 3 here, so that negative 2 becomes a positive 6. And when we are left with that, we get x squared minus 9 on the top. And we've got 3 plus x squared cubed on the bottom. So again, we're interested in when this derivative, this second derivative, changes signs. So set the numerator or denominator equal to 0. As before, this denominator never equals 0. It's always positive. So we only have to worry about the numerator. So we set 6x equal to 0. We set x squared minus 9 equal to 0. We get x equals 0. We get x equals plus or minus 3. So on our G double prime line, we have negative 3 and 0 and 3. These are all places where the second derivative equals 0. Using this as our sign check, maybe at negative 4, we get negative times positive over positive. So 1 negative makes it negative. Maybe if we check negative 1, we get negative times positive. So that's going to be 2 negatives, so that'll be a plus. If we try positive 1, we get positive times negative divided by positive. So that's, again, 1 negative. And then finally, if we try something like positive 4, we get positive times positive divided by positive, no negatives at all. So we see that we have a change in the sign of the second derivative at negative 3, at 0, and at 3. Therefore, 3 POIs at negative 3 comma f of negative 3 at plus or minus, let's save some time there, and also at 0 comma f of 0. Notice I'm not actually evaluating the y value of these points of inflection just for the sake of time. Sometimes they ask for the x value, sometimes they ask for the actual point. If they ask for the point, go ahead and evaluate it. And you should always check these in a graphing calculator, make sure you're doing them right. You can kind of see those points of inflection, but it's, again, the same reason as always, because G double prime changes signs at x equals 0 and plus or minus 3.